Reed-type comparator. Reed-type comparator is a mechanical comparator. For those of you who don't know what comparator means, comparator is a precision instrument used to compare the dimensions of given working component with actual working standard. There are different types of comparators are available. If you're interested to know the construction and working of all the comparators, the link is provided in the description of this video. You can click on the link to watch all the types of comparators. Let's start. You may think why it is called Reed-type comparator? And what is Reed exactly means? Reed is long supporting rod or shaft. In the Reed-type comparator there are reeds, which are used for magnification purpose. Let's see what are the different parts of this comparator. First, reeds. Second, blocks. Third, plunger, which is also called as spindle. Fourth, pointer. Fifth, scale. Out of 4 reeds, 2 placed vertically and 2 placed horizontally, connected between the 2 blocks A and B. Here, A block is fixed block, whereas B block is floating block. Out of 2 vertical reeds, left vertical reed is fixed, and the right vertical reed is movable and is connected to the block B. The floating block is connected to the plunger. As the plunger moves upward, then the floating block moves upward as well. And vertical reed on the right side moves up gradually. This causes the pointer to deflect on the scale. Since we understood the construction and working of the Reed-type mechanical comparator, now let's see how to use it. A working standard will be placed underneath the plunger to take the dimensions as the required dimension. After taking the reading of upper and lower limits of standard's dimension, standard is removed. Now place the workpiece underneath the plunger to take the measurement of the workpiece. Slide the workpiece below the plunger and take the readings. Compare the readings with actual working standards readings. This is how Reed-type mechanical comparator is used. A lever-type comparator is a simple and important type of mechanical comparator. It employs a lever to obtain magnification of plunger movement. It consists of following part: pointer, scale, compression spring, plunger, and stoppers. Working of lever-type comparator. This can be used in 2 ways. First, checking the surface variation of the part from the required dimension. That is to check the upper and lower limit of the given part. And second, to compare the given component with actual standard component present. In this video we will see both. First, a pile of slip gauges of standard dimension is placed on the surface plate below the plunger. What is surface plate? A surface plate is a solid, flat plate used as the main horizontal reference plane for precision inspection, making out and tooling setup. After the pile of slip gauges placed on the surface plate below the plunger, the pointer is set to 0. This can be done by increasing or decreasing plunger length. On the actual comparator, a provision such as adjusting screw will be provided. Now, place the component whose surface variation need to be checked on the surface plate below the plunger by removing the slip gauges and made to slide below the plunger. If any irregularities are present on the surface of the component, plunger moves up and down. This plunger movements are magnified by the lever, which is pivoted at point O, and deflect the pointer on the graduated scale. A compression spring limits the measuring pressure. The magnification achieved depends upon the length of lever on both sides of the pivot. Thus it gives the variation on the surface, which can be represented as upper and lower limit. Another way of using this comparator is direct comparison of the component with the standard required. In this, a standard reference part is taken and is placed below the plunger. As we slide the standard below the plunger, it will give a variation on the surface. This variations are noted down, then the standard is removed and a component to be compared is kept and made to slide below the plunger. The variation shown by the plunger is noted down. Once both variations are noted down, the variations of the component are compared with the variation of the standard. If the component variation are lesser than that of standard, the part is accepted, or else it will be rejected. This method is used during inspection process.
Here is the Johansson Mikrokator. This is a type of mechanical comparator which was developed by the Johansson Ltd company of USA. This instrument uses principle referred as Abramson moment, named after H. Abramson, to obtain high mechanical magnification of the difference in length as compared to the standard. A twisted thin metal strip holds a pointer, which shows the readings on the suitable scale. Since there is no friction involved in the transfer of moment from the strip to the pointer, it is free from backlash. Let us see its construction. The metal strip is twisted and fixed between the two ends as shown. Any longitudinal movement in either direction will cause the central portion of the strip to rotate. One end of the strip is fixed to the adjustable cantilever and the other end is fixed to the spring elbow. The spring elbow, which consists of a flexible strip and a stiff diagonal, acts as a bell crank lever and causes the twisted strip to change its length whenever there is a movement in the plunger. The change in the length will result in a proportional amount of twist of metallic strip. The magnification can be varied by changing the length of the spring elbow. A pull on the metal strip subjects it to tensile force. In order to prevent excessive stress on the central portion of the metal strip, perforations are made in the strip. The plunger rotational movement is arrested by the split washer, which only allows vertical movement of the plunger. Since we understood the construction, now we will see how it is used to compare or its working. The instrument is initially calibrated to the standard and the 0 is set to this value. Instrument also has two pointers which can be set as upper and lower limits. Then the test specimen is placed on the measuring table and made to slide below the plunger of the instrument. Any difference in the measured dimension of the specimen will result in either lowering or rising of the plunger. The lowering and rising of the plunger will make the bell crank lever to move in forward or backward direction, and in turn will twist or untwist the metallic strip. This results in the movement of the pointer, which shows the reading on the appropriate scale. This is how Johansson's Mikrokator works. Hope I have put enough effort to make you understand. If you like my video and want to see more videos like this in the future, then subscribe my channel and turn on the notification. Also like my video and don't forget to comment your opinion in the comment box. Thank you for watching.
Welcome back to Ox Tools. I'm Tom. So what we got today here, this is kind of interesting. This is a Johansson comparator stand, and this was sent to me by a viewer who wishes to remain anonymous. But anyway, this came all the way from Sweden, believe it or not, and it's an original CEJ Johansson comparator stand. So this thing's built like a tank, let me tell you. It was missing a piece, which is what this video is about. We're recreating the anvil that was missing, and we have some machining in this video, and you guys will get to see machining this thing. But we should look at some of the design features of this, which are kind of interesting and notable. And then we have the proper indicator that goes in here as well. So it's got this large 30mm shank. Let's just do the whole thing here while we're at it. Okay, so that's kind of the general layout. But let's take a look at some of the design details. All right, the first thing I want to point out, let's take this out of here. Set that aside. Hopefully you can see in there. Let's see, maybe I can just pop that off and you can see, okay, there you can see it a little bit better. So what they've done, and this is actually a really nice trick here. So you saw that slides on this shaft here, but what they've done is they've relieved the center section here. And the reason for that is that's where the clamp screw is actuating on, and what they want, and this is correct, is they want it to clamp on these outer edges first before the center section, and that gives you the most rigidity when you use one locking screw like that. So it's actually just a subtlety of designing a clamping mechanism like that. And there you can see they've done it in there as well. And it's just a nice touch. I noticed it and I went, oh wow, okay, that's great. So what that means is there's kind of a minimal sliding area, right? But when you lock this down, it locks, and there's no wiggle in that direction. Okay, kind of neat. Then, well, let's we'll go down and we'll take a look at this anvil too. All right, so here's the anvil. Now this is the new one that I made, and like I said, you guys will get to see the machining work on that, in a few minutes here. So what we have here is we have a platen, and then it has some locking screws here, and you can see that they're cone point, and then those reference with those little notches there. And in the video, we show how to accurately position a V or a notch like that in relation to a corner, and that's one of the machining content of this video will show that. So that's kind of neat. And then it has a fine adjust mechanism down here, and let's pop that out of there. So, and there's the relief thing again there. Let's slide this aside. So it's got this is like a micrometer screw here, and it acts on the bottom of this, and that's how you make your fine adjustment there. So instead of a rack and pinion or some, I don't know, kind of awkward setup there, what's nice about this is it's all acting right on the center line. So we lock that down, we leave that loose, and then we make micrometer adjustments here to null the indicator out. So pretty cool. So what do you say we look at some machining content on how to position grooves, and then we got some surface grinder action here doing these long skinny little slots. So don't get to see that very often.
Sigma comparator is a simple but ingenious mechanical comparator developed by Sigma Instrument Company, USA. A linear displacement of a plunger is translated into the movement of a pointer over a calibrated scale. The plunger is the sensing element that is in contact with the workpiece. It moves on the slit washer, which provides frictionless linear movement and also arrests the rotation of the plunger about its axis. A knife edge is screwed onto the plunger, which bears upon the face of moving member of cross strip hinge. This unit comprises of fixed and a moving block, connected by thin flexible strips at a right angle to each other. Whenever the plunger moves up or down, the knife edge drives the moving member of cross strip hinge assembly. This deflects an arm which divides into a Y form. The extreme ends of the Y arm are connected to a driving drum by means of phosphor bronze strip. The movement of the Y arm rotates the driving drum and in turn the pointer spindle. This causes the movement of the pointer over a calibrated scale. The magnification of the instrument is obtained in two stages. In first stage, if the effective length of the Y arm is L and the distance from the hinge pivot to the knife edge is X, then the magnification is L by X. The second stage of magnification is obtained with respect to pointer length R and driving drum radius small r. The magnification is given by R by small r. Overall magnification is given by L by X into R by small r. Since we understood the construction, now we will see how it is used to compare or its working. The instrument is initially calibrated to the standard and the 0 is set to this value. Then the test specimen is placed on the measuring table and made to slide below the plunger of the instrument. Any difference in the measured dimension of the specimen will result in either the lowering or rising of the plunger. The lowering or rising of the plunger will make the knife edge to move up or down, and this makes the movable block to deflect, which in turn deflects the Y arm, which turns the drum, and this results in the movement of the pointer, which shows the reading on the calibrated scale. This is how Sigma comparator works. Here we will see how mechanical optical comparator works, along with basic working principle behind optical comparators and their advantages and disadvantages. Mechanical optical comparator. This is also termed as Cook's optical comparator. As the name of the comparator itself suggests, this has a mechanical part and an optical part. Let us first look at the working principle of optical comparator to understand it better. In an optical comparator, a light source and a reflecting surface such as mirror are used as the optical means. An incident ray will hit the mirror and gets reflected, and this ray will be projected on the scale. If we keep the mirror horizontal and project an incident ray OA at an angle theta to the mirror, then it will get reflected with the same angle theta. The mirror can be tilted, where the tilting of the mirror can be controlled by the measuring plunger. This movement will be projected on the graduated scale, so that if the mirror tilts an angle alpha, then the movement in the reflected ray will be angle 2 alpha. This is the working principle of optical comparators. Since you have got an idea about working principle of optical comparators, now we will see how the mechanical optical comparator works. Mechanical optical comparator is same as optical comparator, but the plunger in the mechanical optical comparator will be replaced with the pivoted lever. Working principle of mechanical optical comparator. The lever acts as the plunger. The mirror is connected to the lever mechanism, which is held by the pivot point. Small displacement of the measuring plunger is initially amplified by a lever mechanism pivoted about a point. The mechanical system causes a plane reflector to tilt about its pivot. The plunger is spring-loaded such that it is biased to exert a downward force on the work part. This bias also enables both positive and negative readings depending on whether the plunger is moving up or down. A beam of light passes through a condenser lens that condenses the beam of light, which helps in rendering of sharper image. A condensed beam of light passes through an index. This image is projected by a projection lens onto the plane mirror. The mirror in turn reflects this image onto the inner surface of the ground glass screen, which has a scale. The scale is set to 0 by inserting a reference gauge below the plunger. Now the reference gauge is taken out and the work part is introduced below the plunger. As the workpiece slides below the plunger, deviation on the workpiece surface causes a small displacement of the plunger, which is amplified by the mechanical lever. The amplified mechanical movement is further amplified by the optical system due to tilting of the plane reflector. The amplification of the comparator is in the two stages. First, mechanical amplification, which is equal to L2 by L1. Second, optical amplification, which is equal to 2L4 by L3. The multiplication factor 2 in the optical amplification is because if the mirror is tilted by theta, then the image is tilted by 2 theta over the scale. Thus, overall magnification of the system is equal to optical magnification into mechanical magnification, which is equal to 2 into L4 by L3 into L2 by L1. This is how mechanical optical comparator works. Now let us see the advantages and disadvantages of optical comparators. Advantages. 1. Higher accuracy will be achieved since it is having very less moving parts. 2. Parallax error will be avoided since the scale can be made to move past a datum line without having any parallax error. 3. Less weight compared to other comparators due to fewer parts. 4. Very suitable for precision measurement due to higher magnification. Disadvantages. 1. Needs a separate electrical source. 2. Optical parts are expensive. 3. They have built-in illuminating device which tends to hit the instrument. 4. Eyepiece type instrument may cause strain on the operator. 5. When the scale is projected on a screen, then it is essential to take the instrument to a dark room in order to take the reading easily.
The Zeiss Ultra Optimeter is another mechanical optical comparator that can provide higher magnification than the simple mechanical optical comparator. It is used to compare the dimensions of given working component with the actual working standard. Zeiss Ultra Optimeter is a type of optical comparator, and it uses two reflecting mirrors to improve the magnification. This is the only difference between Zeiss Ultra Optimeter and other optical comparators. This video will cover the followings about Zeiss Ultra Optimeter. 1. Construction. 2. Working. 3. Advantages and its disadvantages. Let us see the construction of Zeiss Ultra Optimeter. It consists of following parts: light source, green filter, condenser lens, index marking, two reflecting mirrors, that is, M1 and M2, plunger, objective lens, graticule screen, eyepiece. Working of Zeiss Ultra Optimeter. The light rays from the light source passes through the green filter. The function of the green filter is to allow only the green light and filter the remaining all the colors in the light. After passing through the green filter, the light rays pass through the condenser lens. The function of the condenser lens is to focus the rays of light onto the movable mirror, M1. After passing through the condenser lens, the light rays pass through the index marking and carries image of the marking along it. We can see there are two mirrors, M1 and M2. Here, M1 is the movable mirror, which is pivoted at point O, and its movements are controlled by the plunger, which is attached at its bottom. Whereas, mirror M2 is fixed. The light rays from the condenser lens fall on the mirror M1 and get reflected on the mirror M2 and again reflects back to the mirror M1. And the light rays which gets reflected by M1 fall on the objective lens. The objective lens will collect this image and projects it onto the graticule. The graticule is a screen having vertical and horizontal lines like a graph to create coordinate point. This image on the graticule is observed by the eyepiece. By observing the image, we can compare the actual working dimensions with the standard dimensions required. Let us see how magnification is achieved. The factor of magnification depends on the distance between the plunger and the pivot point, O, which we can denote by x. The movement of plunger, which we will denote by letter h, and focal length of the objective lens, which is denoted by letter f. Therefore, magnification is equal to 2 into focal length into angular movement of the mirror divided by plunger movement. Here, angular movement of the mirror is denoted by delta theta. Delta theta is equal to h divided by x. Hence, we can rewrite the above equation as magnification is equal to 2 into f into h divided by x into h. After simplifying, magnification will be equal to 2f divided by x. Advantages of Zeiss Ultra Optimeter. 1. High accuracy. This comparators have very few moving parts and hence gives higher accuracy. 2. No parallax error. The scale can be made pass through datum line and thus have higher range and no parallax error. 3. Higher magnification. Hence, suitable for precision measurements. 4. Optical lever is weightless. 5. Illuminated scale. Since scale is illuminated, it enables reading to be taken, irrespective of room lighting conditions. Disadvantages of Zeiss Ultra Optimeter. 1. As the magnification is high, heat from the lamp, transformers etc. may cause the setting drift. 2. Depends on external electrical power supply. 3. Apparatus is usually bulky and expensive. 4. When scale is projected on a screen, the instrument is to be used in dark room. 5. Instrument is inconvenient for continuous use because the scale is to be viewed through an eyepiece. First we will discuss about the various parts of pneumatic comparator. Then we will see its working. The different type of dimension which can be compared with standard using this comparator. At the end we will see its advantages and disadvantage. If you are new to our channel, consider subscribing to get all the latest videos. And don't forget to give your opinion about this video in the comment section below. Let's start. Construction of the pneumatic comparator. It consists of a compressor. Compressor is the heart of a pneumatic comparator. Compressor compresses atmospheric air and stores it inside the storage tank. Filter. After the compressor, the filter is present. In this filter, all the dust particles present in the air are separated from the air and clean air passes through this filter. Tank. After the air passes through the filter, the air pipe divides into two paths. Some air goes into the tank and some air goes to the gauging head through the orifice. Orifice. This orifice leads air to the second chamber. Manometer. Second chamber is an outlet to a glass manometer tube. Gauging head. The second chamber is also connected by a flexible tube to a gauging head. This gauging head has two restricting jets that are used to check unevenness or irregularities in the workpiece. Working of pneumatic comparator. In this comparator, compressed air is used as an operating medium. At first, the air is compressed in the air compressor. Then the compressed air from the compressor passes through the air filter. All the dust particles present in the air are separated from the air in the air filter, and only pure air passes through the filter. After passing from the filter, the air pipe is divided into two ways. Some air goes to the tank, and some goes to the restricted jet or orifice. As air enters the water tank, bubbles will be created in the tank, and the rest of the air which passes through the orifice reaches the gauging head through a flexible tube. A controlled amount of air passed through the orifice with the required pressure in it. At this time the manometer shows the initial pressure by which the air passes to the gauging head. The workpiece or the job is reciprocated along the gauging head. This gauge head is generally used to examine the internal diameter of a cylinder, whether it has irregularities or not, in its internal diameter. This gauge head is inserted into the cylinder, and both jets in the gauge head faces towards the internal wall of the cylinder. The internal wall of the cylinder restricts the air coming out of the jet of the gauging head. Based on the gap between the jet and internal wall of the cylinder, back pressure will be created as the internal wall restricts the air coming from the jet. When the back pressure is created, the air which is passing through the gauging head will return back and it will go inside the manometer tube, and this backflow of air will push down the water inside the manometer. At first, a standard workpiece is taken in which the internal wall is perfectly flat. This standard workpiece is used to calibrate the pneumatic comparator. Using this standard workpiece, the water height as the manometer is adjusted so that it is equal to the height of water in the tank. This standard workpiece is known as a reference workpiece because it is used to get the reference pressure in the manometer. When the gauge head of the pneumatic comparator is placed inside a cylinder which is to be examined, the air hits the internal wall of the cylinder, and if there are any irregularities in the internal wall, the back pressure in the comparator is created and the water inside the manometer is pushed down. Hence, the water level inside the manometer falls, and we get a height difference between the water level of tank and water level of the manometer. This height difference is denoted by delta H. So if the delta H value is high, then we can say that more amount of roughness is there at the position of the cylinder where the gauge head is placed. After the gauge head is placed in different positions inside the cylinder, and delta H is noted for different points so that roughness throughout the cylinder can be measured. If delta H is high for different points inside the workpiece, then this workpiece needs to be rejected. Pneumatic comparator is used when a large number of cylinders or workpiece needs to be tested. That is, when there is the mass production of the workpiece and quality inspection needs to be done. Applications of pneumatic comparator. Cylindricity. The example used in this video is of checking cylindricity. Ovality. To check ovality, we need to rotate the gauging head inside the part. This will give all the variation on the circumference of the part. Similarly, this comparator can be used to check other dimensions like straightness, external diameter, etc. Advantages. It is cheaper, simple to operate, and the cost is low. It is free from mechanical hysteresis and wear. The magnification can be obtained as high as 10,000 times. The gauging member is not in direct contact with the work. Tapers and ovality can be easily detected. The method is self-cleaning due to continuous flow of air through the jets, and this makes the method ideal to be used on shop floor for online controls. Disadvantages. They are very sensitive to temperature and humidity changes. The accuracy may be influenced by the surface roughness of the component being checked. Different gauging heads are needed for different jobs. Auxiliary equipment such as air filters, pressure gauges and regulators are needed. Non-uniformity of scale is a peculiar aspect of air gauging, as the variation of back pressure is linear over only a small range of the orifice size variation.